Professor Godfried Toussaint has multiple prestigious affiliations, and his research interests include comparative musicology with special emphasis on the mathematical and computational aspects of rhythm, and he wrote a book called The Geometry of Musical Rhythm. Toussaint's page on comparative musicology has right at the beginning a 3/2 son clave spelled out around a circle, in other words counting modulo 16, so it's going 1 0 0 1 0 0 1 0 0 0 1 0 1 0 0 0, which is one of the most popular clave rhythms in the world. He has published widely on rhythms, and we're going to look carefully at this particular paper on the Euclidean algorithm. Toussaint asks, what do African rhythms, spallation neutron source accelerators in nuclear physics, string theory in computer science, and an ancient algorithm described by Euclid have in common? Here's what a spallation neutron source looks like. The answer Toussaint found was in a paper by Bjorklund, who was trying to solve a problem about high voltage power supplies in the spallation neutron source. The solution was to construct a binary sequence of n bits with k1s such that the k1s are distributed as evenly as possible among the zeros. The algorithm is closely related to the Euclidean algorithm, and Toussaint decided to call the rhythms generated by Bjorklund's algorithm Euclidean rhythms, and he denotes them by EKN, where k is the number of ones and n is the length of the sequence. So he gives as an example E513, and he also uses this diagrammatic convention for a cyclic binary sequence. On the left, he has E38, which is the Cuban tresillo, and on the right is E58, which is the Cuban cinquillo. And he points out that E58 is the hand clapping pattern in Elvis Presley's Hound Dog. The numerological mysticism of the esoteric teaching of George Gurdjieff includes the Enneagram, which is calculated by taking the reciprocal of the number 7 in decimal expansion, which is 1, 4, 2, 8, 5, 7, and then start over again, and put that around a circle and fill in the remaining positions with 3, 6, and 9. You get this very nice symmetrical diagram. Gurdjieff develops an entire cosmological system on this diagram, but in any case, that's numerology. If you start with a smaller number and a larger number and repeatedly subtract the smaller number from the larger number, you may or may not have a remainder from which you cannot subtract another copy of the smaller number. If the remainder is 0, then you say the smaller number is a divisor of the larger number. Given two larger numbers, you can always ask whether there is a divisor for both of them, in which case you say it is a common divisor of both of them. A mathematical question is there a greatest common divisor amongst all the divisors of two given larger numbers? Euclid recorded an algorithm for finding the greatest common divisor of two larger numbers. So, for example, given 10 and 7, you can subtract 7 from 10 one time with a remainder of 3. Then you can subtract the 3 from the 7 two times, as shown in red, with a remainder of 1. And then you can subtract that 1 from 3 times without remainder. So Euclid concludes that 1 is the greatest common divisor of 7 and 10. Another fellow named Nicomachus started with 49 and 21. He subtracted 21 from 49 2 times, with a remainder of 7. Then he subtracted the 7 from 21 3 times, with 0 remainder, and concluded that 7 is the greatest common divisor of 21 and 49. Among many alternatives, here are 3 ways to implement the Euclidean algorithm in Python. It's convenient to have a switch function that arranges for the first argument to be smaller than the second argument. GCD1 is an iteration using a while statement, and GCD1 of 22, 39, 61 gives a greatest common divisor of 1 in 6 steps. GCD2 uses a counter to tell you how many steps, so I have to make sure that counter is initialized at 0. And GCD2 of 22, 39, 61 is also giving greatest common divisor of 1, but it shows that there are 6 steps. GCD3 is an iteration, again with a while statement, but it's very cute. The mathematical paper by Bjorklund, referenced by Toussaint, is a beautiful piece of work, including the algorithm invented by Bjorklund, which is shown here in C-like code. And Bjorklund proves a theorem that this is an efficient algorithm. And the proof involves a serious reference to the Fibonacci sequences, which makes it really interesting. Let's see how n equals 13 and k equals 5 is calculated by the Bjorklund algorithm. So we put 5 ones and the balance in zeros: 6, 7, 8, 9, 10, 11, 12, 13. And he says take the zeros starting at the bottom 0 and bring them over here like this. And that uses up 5 zeros. And then he says take the next 3 and bring them down like this, so that all told at this point we've used up 8 items. Now there are 2 items left here, so we bring those down like this. And now there's 1 item left, so he says stop. And then read off the answer from the last row going up to the stop row: 1, 0, 0, 1, 0, and then another 1, 0, 0, 1, 0, and then the stop row is 1, 0, 0. So you end up with 1, 0, 0, 1, 0, 1, 0, 0, 1, 0, 1, 0, 0. And that's 13 items, and they alternate: a 2, a 1, a 2, a 1, and then a 2. And then, of course, since it's a cyclical binary sequence, you are going to get a double 0, but you can't do any better than that. Let's try the same thing with n equals 8 and k equals 5. So you go 1, 2, 3, 4, 5, 6, 7, 8. And then he says take the zeros and bring them down: 0, 0, and 0. And that used up 3 items. You've got 2 items left here, so you bring these down: a 1 and a 1. And now you have 1 item left here, so he says stop. and read off the answer as 1, 0, 1, 1, 0, 1, and then the stop row 1, 0. And that's very even, and that is Cinquillo. Programmer Brian House re-implemented Bjorklund's algorithm in Python, including the definition of recursive function build, which calls itself either here or here. But he defined that inside of the main function Bjorklund, I guess to avoid global variables. But anyhow, I redid the code a little bit, and I extracted build. I call it BLD. It has a couple of more parameters, and then it's called once by the main function bj. We can confirm the manual calculations of the Bjorklund algorithm by compiling and running the Python code with bj open paren 13, 5 close paren, and there is the same pattern calculated by hand, and likewise bj open paren 8, 5, and we get the Cinquillo rhythm. What we do with this is show intermediate results by setting the print flag equal to 1, p flag equal 1, and repeating those calculations, bj open paren 13, 5 close paren, and you see intermediate results, and there's a certain amount of repetition, and I'll tell you what we're going to do with that in a moment, but let me just show the same intermediate results for the Cinquillo 8, 5. I took the output of bj 8, 5 and created an array in Uno code where I removed repetitions of most of the intermediate results but duplicated the final result 4 times to show the Cinquillo pattern over and over again. And the code for running that array is called play Toussaint, in which I added a couple of little things in between to make it more interesting.